Hey guys, tonight we step far, far back, so far back that your human brain almost short circuits, trying to hold the number in your head. Before starting, subscribe the channel. The year is 1800,000 BCE. No pyramids, no dinosaurs, no fish, no plants, not even a single bug buzzing around, just a planet, wrapped in thick clouds, seas stretching endlessly, and a patchwork of ancient landmasses grinding toward each other like tectonic bumper cars. You stand, or more accurately, you float in imagination above a globe that looks familiar in outline, but completely alien in texture. The surface is scarred with volcanic scars, smoking ridges, and endless crags where molten rock once spilled. The air carries far less oxygen than you enjoy today, and breathing it would be a fast way to pass out. You probably won't survive this, but hey, let's keep going anyway. Down below, something incredible is happening. The first true supercontinent, later called Columbia, is welding itself together. What were once scattered, wandering fragments of continental crust, thick slabs of ancient rock called cretons, are colliding. Think of them as the Earth's old-school Lego pieces, finally snapping into a single giant build. Mountain belts rise like colossal wrinkles where they crash, while other regions slump into shallow seas. From a planetary scale, the world is trying out a new design. One massive continent surrounded by a single vast ocean. This isn't just geology trivia, it's a turning point in Earth's history. Columbia will shape the chemistry of the oceans, the flow of heat inside the mantle, and even the future of life itself. So before we sink deeper into the fires, ridges, and microbial mats of this alien time, let's pause. If you're watching, drop your current location and local time in the comments. Imagine what your spot looked like back in 1.8 billion BCE when it was part of Columbia's crust. And remember, tonight's theme is 1800,000 BCE, the first supercontinent, Columbia. Close your eyes, settle in and drift across that barren, ancient world. Sweet dreams are built on the strangest of foundations. From here the story slides straight into the birth of Columbia itself. No pause, no break. Just the Earth pulling its plates together in a slow-motion collision of unimaginable scale. You sense the weight of continents converging, Laurentia moving in from one side, Baltica from another, Siberia inching closer. Imagine the grinding roar as slabs of granite, thousands of kilometers long, smash together, pushing up jagged peaks that stretch higher than Everest's future cousins. Beneath them, subduction zones gulp down oceanic crust like conveyor belts feeding the mantle. Each collision welds the jigsaw puzzle tighter until the pieces lock into something bigger than anything Earth has seen before. The land under your feet, or where feet would one day evolve, is hard, ancient, stable. These cratons, the roots of continents, formed long before Columbia, back when the Earth was still bleeding heat furiously. Now at last, they've found partners to cling to. The Yilgarn Craton of Australia, the Kupval Craton of South Africa, the Canadian Shield. They are no longer lonely fragments but part of one global congregation. What does the air feel like above this stitched-together surface? Thin, harsh, and chemically strange. Oxygen has only recently begun to rise from near-zero levels, thanks to cyanobacteria's tireless photosynthesis. But for you that still means a faint whisper compared to modern lungs. Your chest tightens. You'd need an oxygen tank just to last a few minutes. The dominant gases are nitrogen and carbon dioxide, with a haze that scatters the sun's light into a duller glow. The sky often carries a faint reddish tint, filtered by dust from endless volcanoes. On the horizon, those volcanoes spit lava fountains into the air. Supercontinent building is never gentle, it's a violent, molten business. You would see black basalt flows hardening across vast plains, while ash clouds roll overhead like bruised storm fronts. Between eruptions, shallow seas lap at irregular coastlines, leaving tidal flats where microbial mats spread like carpets of greenish slime. They are the closest thing to life you'll see with the naked eye. It's almost comic how empty the world is. No trees, no fish, no birds overhead. Just stone, water, fire, and slime. And yet, this emptiness is deceptive, because the assembly of Columbia is setting the stage for all of that to come. By welding together the continents daintily heat flow inside Earth's mantle. They slow the rate of crust formation. They alter ocean circulation. In short, Columbia is turning Earth into the kind of planet where complexity might one day stand a chance. The scale of time here is what really bends your mind. Columbia won't finish assembling overnight. It takes hundreds of millions of years. Imagine waiting for a mountain to rise not in decades, but in geological heartbeats that span tens of millions of years each. Blink, and nothing changes. Wait 100 million years, and entire oceans close up while ranges the size of the Himalayas crumble flat again. Still, by 1.8 billion years ago, the process has largely succeeded. Columbia dominates the globe, stretching across an equatorial belt. Some models imagine it shaped like a giant donut, others picture it as more of a long chain of landmasses. However you visualize it, it's the largest thing your planet has ever assembled. And you hovering there in imagination are one of the few creatures in the universe to bear witness to it. Your mind maps the lines of cratons locking together, Laurentia tucked beside Baltica, Amazonia squeezed against West Africa, Siberia slotted toward the northeast. Like a puzzle, the fit is clear when you see it from above. Down below, the planet groans with the strain, faults rupture, earthquakes hammer coastlines, lava seeps into rifts that almost but not quite tear the new supercontinent back apart. Rivers of molten basalt stretch for hundreds of kilometers, glowing red in the dark. Cooling cracks through them create hexagonal columns, the same patterns you might one day see at the Giant's Causeway in Ireland. Only here it covers entire provinces. A modern joke comes to mind: you'd never want to buy real estate here. Your house might sit on stable granite one year and be swallowed by lava the next. But then again, there aren't any real estate agents either. As Columbia stabilizes, its interior becomes harsh and dry. With so much land clustered together, rainfall struggles to reach deep inland. The coasts host microbial reefs. The interiors become arid wastelands of bare rock. Dust storms sweep across them, carrying fine sediment into shallow basins. Over time, these deposits lithify into red sandstones and shales, some of the oldest rocks that geologists today can still point to as Columbia's signature. Standing on this surface, you would feel both awe and crushing loneliness. The horizon is silent except for the hiss of wind and the distant rumble of volcanism. No chirping insects, no rustling plants, just the raw heartbeat of a planet building its foundation. And yet in that silence you realize, this is the world's first experiment with continental unity. Without Columbia, there would be no Rodinia, no Pangaea, no familiar map of Earth at all. Remember this moment, because Columbia is where the story of Earth's supercontinents truly begins. And waiting continues. The birth of Columbia was not a single fiery explosion, but rather the slow, grinding embrace of Earth's oldest land fragments, the cratons. These were the battered survivors of an earlier, hotter Earth, each one a thick root of continental crust that had managed to endure billions of years of tectonic chaos. To you they seem almost indestructible, massive slabs of granite and gneiss, stretching hundreds of kilometers across, their foundations plunging deep into the mantle like anchors. You picture them as wanderers. Laurentia, the ancient heart of what would someday be North America, drifting like a lone raft across an oceanic abyss. Baltica, a future piece of Europe, trailing in its wake. Amazonia, carrying the seeds of South America. Siberia, Australia, India, all separated, yet destined to converge. If you hovered above the planet on some cosmic viewing platform, you'd watch these giants inching toward each other at the speed your fingernails grow. Sounds laughably slow, but wait a few 100 million years and the oceans between them close, as if the Earth is pulling a zipper shut. How do these collisions actually happen? Plate tectonics, the restless engine beneath your imaginary boots, never sleeps. Where oceanic crust sinks beneath continental slabs in subduction zones, trenches form, volcanoes rise, the seafloor bends downward like conveyor belts feeding rock into the mantle. At the same time, the continents themselves are propelled toward each other, pushed by mantle convection cells that churn like vast boiling pots of stone. Over millions of years, that steady push slams them together. You'd hear the consequences as thunder without clouds. Earthquakes echo across proto-oceans, mountains crumple up in slow motion. When Laurentia collides with Amazonia, imagine continents grinding like two giant gears, their leading edges crushed into ribbons of folded rock. Fault zones stretch for thousands of kilometers, filled with molten intrusions that cool into veins of granite. These veins are still visible today in Canada, Brazil and Scandinavia, silent witnesses of Columbia's birth. The scars of these collisions are preserved in what geologists now call orogenic belts, ancient mountain chains long since worn down by weathering. In their day, though, they were colossal, entire Himalayan-scale ranges rose where cratons smashed together. Their summits would have been jagged, raw and almost constantly shaken by tremors. Rivers, if any existed in those barren times, would have carried sediments from their flanks into shallow inland seas. Layer by layer, these sediments compacted into sandstones and shales, archives of the violence above. The sheer scale of Columbia begins to reveal itself here. By about 1.8 billion years ago, the core of this new supercontinent stretched across the equator. Some reconstructions suggest it spanned from pole to pole, perhaps 12,000 kilometers in length. Imagine standing at one edge and realizing it would take more than 100 modern countries lined up side by side to cross it, and yet without oceans between, its interior was locked away from moisture. You'd find parched deserts in the heartland, broken only by scattered volcanic provinces and shallow basins where occasional rain pooled. Now a reality check. If you were really there, you'd have almost no landmarks to guide you, no forests, no grass, no animals moving across the land, just endless rock under a sun that looked much like today's but shone on a planet far less forgiving. Your modern hiking boots would crunch on loose gravel made of volcanic glass, your lungs would burn from the lack of oxygen, and your water bottle useless. The seas were salty and sometimes toxic, laced with iron and sulfur compounds. Forget sipping it, even microbes had to fight hard to survive in those waters. Still, the continents did what continents always do, they fused. Laurentia welded to Baltica in a long suture zone, Amazonia squeezed in from the south, Siberia locked into position, and piece by piece the puzzle became whole. When geologists today map these connections, they use ancient magnetic minerals as tiny compasses, trapped in rocks. Those minerals point toward the Earth's magnetic field at the time of their formation. By comparing their directions across different cratons, scientists can tell when two pieces must have lain side by side. It's a detective game played across billions of years, and the solution always leads back to Columbia. Standing on such a sutured boundary, you would feel the ground beneath your feet telling its story. Bands of metamorphic rock show where crust was squeezed until it recrystallized. Folds twist in graceful arcs, frozen mid-crumple, intrusions of granite cut through them like scars. If you ran your hands across the stone, you'd be touching the fingerprints of two continents' collision. It's tempting to call Columbia a peaceful union, but nothing about it was peaceful. Every joining came with fire. Subduction zones churned out volcanic arcs, belts of volcanoes spewing ash that blotted out the sun. Flood basalt smothered the land in dark lava, sometimes stretching thousands of kilometers across. Earthquakes would have been near constant, small tremors daily, catastrophic rumbles every few thousand years. If you had a medieval village here, not that you could, it would be flattened faster than you could say Columbia. But slowly, through this relentless destruction, a continent bigger than any before emerged. You step back, hovering again in imagination, and watch Earth's crust settle into this new arrangement. Oceans shrink, mountain ranges cool, volcanic arcs subside, the collisions quiet down, not forever, but long enough for Columbia to hold its place as Earth's reigning landmass for nearly 300 million years. Here's the ironic part. All of this fury, mountains rising, lava flowing, crust welding, sets the stage for calm. Once the pieces of Columbia locked together, they formed a vast, stable platform. For the first time, Earth had a true continental nucleus big enough to anchor weather, oceans, and eventually life's expansion. Without it, the world might have remained a scattered archipelago forever, never giving complexity the space it needed. And if you're wondering, yes, Columbia is long gone now. It fractured into new supercontinents, its pieces wandering once again, but when you walk through the Canadian Shield or the Amazon Craton today, you're literally stepping on fragments of this first global experiment. Beneath your boots, the rocks whisper, "We were here when the first supercontinent rose." You hover again, this time closer to the crust itself, where the secret of Columbia's growth is hidden, not in the surface mountains alone, but in the invisible machinery of plate tectonics. It's easy to forget that continents are not fixed objects, but passengers riding on enormous slabs of lithosphere. These slabs drift, collide, sink, and rise as the mantle beneath them churns with unstoppable convection. Think of it like a giant slow-motion lava lamp, hot plumes rising, cold slabs sinking, the whole cycle pushing continents around like lazy corks on a boiling pot. In the world of 1.8 billion years ago, those corks were colliding with particular intensity. Subduction zones, those gaping mouths along oceanic margins, were the main highways of destruction. Imagine the edge of a continent where the seafloor plunges downward into the mantle. Trenches thousands of kilometers long carved deep gashes into the ocean floor, places where rock was recycled into Earth's interior. Every time an oceanic plate sank, it dragged the attached continent closer to its neighbors, setting up collisions that stitched together Columbia. You picture one of those collisions, Laurentia on one side, Siberia on the other. The seafloor between them shrinks, millimeter by millimeter, year by year, until it's gone, and then, suddenly in geological terms, the two cratons slam into each other. Subduction grinds to a halt, the trench collapses, and a mountain belt erupts in its place. The sound, imagine the world's loudest earthquake, magnified over millions of years. Your modern nerves wouldn't last a second standing anywhere near it. The crust responds violently. Some pieces crumple upward into mountains, while others are shoved sideways for hundreds of kilometers along strike-slip faults. In the chaos, magma intrudes upward, cooling into granite batholiths, the size of small countries. If you could stand there in safety, and ignoring the lack of breathable air, you'd see entire valleys glowing at night from rivers of magma. Jokes aside, you'd need more than marshmallows to roast here. Tectonics doesn't only build mountains, it rips them apart. Even as Columbia was assembling, rifts threatened to tear it open. Mantle plumes, columns of abnormally hot rock punched through the crust from below. At the surface, these plumes triggered massive outpourings of basalt lava, sometimes covering thousands of square kilometers in weeks. From orbit, they'd look like glowing scars across the supercontinent's skin. Some plumes succeeded in cracking open oceans, others stalled, leaving behind volcanic plateaus. Either way, they kept Columbia's crust restless, alive. And then there were the sutures, the stitches where cratons locked. These weren't neat, clean joins, they were messy seams, filled with deformed rock, metamorphic zones, and fault systems that shifted long after the main collision ended. Walk across one today, in Canada or Greenland, and you'd find belts of schist and gneiss twisted like taffy, the unmistakable signs of tectonic pressure. Each suture was a reminder of the violence required to make something whole. From above, Columbia's geography began to take shape. Imagine a supercontinent stretched wide along the equator, with long mountain ranges marking its collision scars, vast plains of granite stabilized between them, punctuated by volcanic arcs that still smoke. Off its coasts, the last remnants of ancient oceans swirled, their currents bending around this new giant landmass. If you had a god's eye view, you'd trace the outline: Laurentia at the core, Amazonia pressed against it, Baltica and Siberia angled nearby, Australia and India tucked along the edges. The puzzle looked clumsy, but it held together. The mechanics of this process, subduction, collision, rifting, were not random. They were guided by the mantle's convection cycles, which operated on scales so large you can barely picture them. Heat from Earth's core drives this entire system. Picture an inner furnace pumping out energy, keeping the mantle soft enough to flow. Without that heat, plates would freeze in place, continents would stagnate, and supercontinents like Columbia would never form. One irony here is that the very same tectonic violence that makes Earth uncomfortable for survival is also what makes it habitable at all. Recycling crust through subduction keeps the atmosphere balanced over eons. Volcanic eruptions pump gases that shape climate. Colliding continents create shallow seas where life can flourish. If Earth had a more static crust, like Mars or the Moon, it might still be a barren rock. So yes, Columbia's assembly was messy, but without it, you wouldn't be here imagining it. Picture yourself camping on Columbia's edge. A terrible idea, but go with it. To the west, a volcanic arc glows red under a hazy sky. To the east, mountains rise like serrated knives, their flanks collapsing into rubble that washes into shallow basins. Underfoot, the ground hums with tremors, sometimes gentle, sometimes sharp enough to knock you flat. Every few months, ashfall blankets your campsite in gray dust, burying whatever gear you left behind. And if you thought earthquakes were a problem today, try living where cratons collide. Your tent would last about 10 minutes. From a distance, however, there's a strange beauty to it. The planet is sculpting itself into a form that will last. Columbia isn't a fleeting experiment, it will dominate Earth. For nearly 300 million years, the crust beneath you is thickening, becoming more resistant to recycling. Mountains, though ephemeral in the short view, are feeding sediments that will one day become stable platforms for future continents. This is Earth, in the act of becoming itself. You might even laugh at the irony. Here you are, floating in imagination above a planet that looks desolate, violent, and unwelcoming, yet everything happening is laying the groundwork for forests, rivers, and eventually the small annoyance of mosquitoes. Without Columbia's tectonic gymnastics, there would be no continents big enough to support ecosystems. In a sense, you owe your entire existence to these brutal collisions. And as the grinding continues, Columbia locks tighter, craton by craton, subduction trench by trench. The first true supercontinent becomes real. The mantle keeps pushing, the crust keeps groaning, and the Earth, never content with small things, settles into its first grand design. Now that Columbia is finally welded into a recognizable shape, you float higher, tracing its outlines like a cartographer of deep time. The geography of this first supercontinent is alien but oddly familiar in concept. A single, immense landmass dominating Earth's face, fringed by the restless ocean that encircles it. Imagine looking down on a globe where almost all the continental crust is stitched together, leaving one giant body of land surrounded by a single vast sea. It's not quite the modern Atlantic and Pacific split, it's more like one colossal panthalassa, an ancestor of future world oceans. The sheer size of Columbia is staggering. Reconstructions suggest it sprawled thousands of kilometers along the equator, maybe from pole to pole. Think of it as a mega-continent that would have dwarfed anything you see on a classroom globe today. North America's future core, Laurentia, anchored its heart, Baltica pressed in nearby, Siberia latched to the northeast, Amazonia and West Africa squeezed against its southern edge, and Australia and India clung as appendages. You wouldn't recognize them by shape yet, they were distorted fragments compared to their modern outlines, but they were all there, fused into a monstrous continental quilt. From your vantage, the continent's edges are jagged with mountain belts. These are not gentle Appalachian ridges softened by time, they're raw, towering ranges, sharp as knives, the aftermath of continent-on-continent collisions. Some peaks would have rivaled the Himalayas in scale, casting shadows across valleys filled with volcanic ash and debris. Yet unlike modern mountain chains adorned with forests and snowcaps, Columbia's ridges were bare, no greenery softened them, just naked rock glowing in the sun, broken only by patches of microbial mats in lowlands where water pooled. The interior of Columbia tells a different story. Once you leave the coasts, moisture becomes scarce. With so much landmass concentrated, rainfall from oceans couldn't easily penetrate deep inland. The result was a dry, barren heartland, a desert of stone and dust, punctuated by ephemeral lakes that appeared and vanished with shifts in climate. Winds scoured the plains, carving dunes from loose sediment. If you were wandering across this wasteland, the silence would be overwhelming. No bird cries, no insect hum, only the hiss of sand carried by gusts. Along the coasts, shallow seas lapped at the edges of the continent. These were warm, sunlit waters, sometimes murky with volcanic debris, sometimes iron-rich and tinted a deep green. Here, microbial mats clung stubbornly to tidal flats, building structures known today as stromatolites. Layer by layer, mats of cyanobacteria trapped sediments, forming mounds that grew upward with time. If you crouched close, you'd see tiny bubbles of oxygen trickling into the water, unimpressive at the moment, but world-changing in consequence. Circling the continent, the global ocean moved differently than today's currents. With one landmass dominating the surface, circulation was streamlined. Warm currents hugged the equatorial coasts, while cold currents slid past polar margins. This simple pattern redistributed unevenly, leaving Columbia's equator warm but baking, and its interiors bone dry. The poles, by contrast, likely experienced cold upwellings. No ice sheets yet, but a chill compared to the equatorial belt. Here's the part that makes you smirk. Modern maps have neat borders, convenient color codes, and political divisions. Columbia's map would look like an abstract jigsaw puzzle of scars. Mountains, volcanoes, and basins would be the only features you could label. Want to visit Australia? Sure, but it's jammed against India and Antarctica, nothing like its lonely spot in today's oceans. Imagine trying to explain that to a travel agent. I'd like a cruise to Australia, but only when it's attached to Siberia, thanks. Even Columbia's coastline was unstable. Tectonic activity never truly stopped, so rifts periodically opened along its edges, threatening to peel fragments away. In some areas, massive volcanic provinces lined the shores, creating plateaus of solidified lava that jutted into the ocean. In others, subduction zones dragged oceanic crust downward, generating deep trenches and arcs of volcanic islands. Picture a coastline that changes dramatically over 1 million years. 1 century you have a shallow bay, The next you have a volcanic plateau. Time moved at a pace that would make modern humans dizzy. And yet, in spite of its volatility, Columbia's geography was crucial for Earth's development. By clustering the continents together, it created new circulation patterns for both air and sea. It also concentrated land-based weathering processes, rain that did fall on mountain slopes, carved valleys, washing minerals into the ocean. These nutrients fed cyanobacteria, which in turn pumped more oxygen into the atmosphere. A simple chain of events, but one that reshaped the planet forever. Geography also determined climate. Large land masses reflect sunlight differently than oceans, altering the balance of heat absorbed and released. Columbia's wide surface probably created hotter summers and colder winters than Earth had experienced before. Without vegetation to anchor soils, erosion ran rampant, filling shallow seas with sediments. Imagine endless mudflats stretching to the horizon. The beach experience of Columbia, not exactly a tourist destination, unless you're into slime. Looking at Columbia from above, the contrasts are stark. Along the edges, dynamic coastlines and microbial reefs. Inland, barren deserts and sharp mountains. Across the surface, scars of volcanism, and all of it surrounded by a monotonous ocean, stretching farther than you can see. The Earth of 1.8 billion years ago had finally achieved continental unity, but it was a unity forged in harshness, a testing ground for stability that would last only until tectonics tore it apart again. Still, Columbia's geography wasn't just a fleeting arrangement. Its position and shape shaped the chemistry of the oceans, the flow of heat in the mantle, and the possibilities of life. For hundreds of millions of years, this supercontinent ruled Earth's surface, a silent rocky monarch, presiding over empty skies and microbial seas. If Columbia's outline was a map of scars, then its mountains were the loud punctuation marks, towering monuments to tectonic violence. You wander across one of these collision zones, where two cratons slam together with unstoppable force. Imagine the ground beneath you folded like a rug being pushed from both ends. Layers of ancient rock buckle, tilt and crumple into tight curves. Granite veins slice through them like molten stitches, reminders of magma that once surged upward through every crack. These were among the earliest true mountain ranges the planet had ever seen, not little volcanic cones rising alone in the ocean, but belts of jagged peaks stretching for thousands of kilometers. When Laurentia fused with Amazonia, entire ranges soared skyward. When Baltica and Siberia locked in, more rose to join them. Each collision zone became a colossal orogeny, a mountain-building event whose ruins you can still touch today in Canada, Brazil, and Scandinavia. From a modern perspective, the scale is hard to grasp. The Himalayas rise about 9 kilometers at their highest. Columbia's ranges may have matched or exceeded that, though erosion has long since whittled them down. Picture valleys so deep you'd lose sight of the horizon, peaks so sharp they'd shred clouds, and slopes covered in rubble that tumbled endlessly downslope. No greenery softened the edges, no forests blanketed the foothills, just stark, bare stone, gleaming under a hazy red sky. What would it feel like standing there? The ground never entirely still. Quakes rattled through these belts, sometimes small tremors, sometimes continent-shaking rumbles. Massive landslides must have been common, sending rivers of debris crashing downslope. In your imagination, you press your hand to the rock and feel warmth pulsing up from below, magma chambers feeding volcanic eruptions that often accompanied the uplift, and above all, silence. No bird song, no mammal calls, only the wind keening through empty passes. One of the strangest sights would have been the constant metamorphosis of rock. Under the pressure of collision, ordinary sedimentary layers transformed into new crystalline forms. Shale recrystallized into slate, then schist, then gleaming gneiss with zebra-striped bands. Limestone metamorphosed into marble. If you could watch it in accelerated time, you'd see the very fabric of stone reknitting itself under pressure and heat. Geologists today still marvel at these rocks, slicing them into thin sections to study under microscopes. Every fold and crystal records the agony of Columbia's assembly. Rivers carved through these fresh mountains, carrying loads of sediment toward the shallow seas ringing Columbia's coasts. Over millions of years, these rivers filled basins with thick piles of sandstone, mudstone, and conglomerate. If you trace those rocks today in North America or Africa, you are literally holding the weathered remains of Columbia's mountains in your hand. Your palm closes around grains that once sat on slopes rivaling Everest's ancestors. Now, a quick reality check. If you were a tourist in this time, you would not last long. no oxygen to breathe, constant quakes to shake your camp, volcanoes to ash out the sky. Forget ski resorts, your chalet would be buried in lava before you checked out. But here's the irony, these mountains weren't just hazards, they were crucial engines of Earth's stability. Weathering of fresh rock pulled carbon dioxide out of the atmosphere, storing it as carbonates in oceans. This helped regulate the planet's greenhouse balance, cooling Earth just enough to keep oceans liquid without freezing over entirely. Without mountain building, Earth's climate could have spun wildly out of control. And let's not forget the metals. These mountain belts were factories for mineral deposits. When two cratons collided, heat and fluids coursed through their sutures, concentrating gold, copper, nickel, and rare elements in veins. Billions of years later, humans would dig into those very belts to fuel industry. Your phone's wiring, your laptop circuits, they might carry atoms forged in Colombia's ancient mountains. Talk about a deep supply chain. From a broader view, Colombia's mountains stitched the supercontinent together. Each orogeny acted like a rivet in a steel frame, locking the puzzle pieces more tightly. Without them, the cratons might have drifted apart again too quickly. Instead, Columbia held firm for hundreds of millions of years, its interior shielded by the thick crust beneath these belts. The mountains themselves eroded, but the sutures they left behind became the backbone of continents we still recognize today. Imagine walking along one of those sutures, straddling the seam where two worlds became one. To your left, rocks from one craton, ancient granite, 3 billion years old. To your right, rocks just as old, but with different origins. And between them, a belt of twisted metamorphic stone, evidence of the collision that bound them. If you could plant a flag there, it would mark the birthplace of modern continental crust. In truth, Colombia's mountain belts were less like picturesque landscapes and more like war zones in slow motion. Continents clashed, crust shattered, magma intruded, and mountains rose. But out of that chaos came stability. Out of violence came the foundations of the continents we walk on today. As Colombia rose into its full stature, one force never stopped flexing its muscles: volcanism. You've seen the mountains that came from collisions, but now you watch the sky darken with ash as volcanoes flare across the supercontinent. They weren't isolated cones like Vesuvius or Fuji, though a few such peaks existed, but more often, vast volcanic provinces that poured rivers of lava hundreds of kilometers long. Imagine entire regions glowing red at night, not from city lights but from sheets of molten basalt flowing across the surface. The cause was tectonics in overdrive. Subduction zones circled Colombia's edges, swallowing oceanic crust into the mantle. Each sinking slab triggered arcs of volcanoes, spewing gases and ash into the sky. Along rifts inside the continent, mantle plumes pushed upward, splitting the crust like cracks in a windshield. These plumes didn't politely ooze lava, they unleashed flood basalts, giant outpourings that buried landscapes under black rock several kilometers thick. In the geological record, you can still trace these scars in places like India's Darwar Craton and parts of Canada. If you stood near one of these provinces, an objectively terrible idea, the scene would overwhelm every sense. The ground shuddered as fissures split open, fountains of lava spraying upward dozens of meters. Heat scorched the air, making it shimmer like glass. Ash clouds rolled overhead, blotting out the weak sunlight, turning noon into a dusky twilight. The smell, sulfur, acrid and choking, mixed with scorched stone. Breathing it would be like inhaling sandpaper laced with acid. Your boots would soften and melt within minutes if you strayed too close. And yet, there was a rhythm to it. Volcanism wasn't a single, constant eruption. It pulsed over millions of years. A flood basalt might cover half a continent, then die down, leaving behind plateaus of black rock that stretched as far as you could see. Over time, rain and wind would carve them into rugged mesas, but in their youth they were flat, bleak expanses, like planetary parking lots of cooled lava. Other eruptions clustered into volcanic arcs, chains of peaks rising above subduction zones, their slopes built from layer upon layer of ash and lava. One peculiar feature of this volcanism was its role in shaping the atmosphere. Every eruption belched gases, carbon dioxide, sulfur dioxide and water vapor into the air. Carbon dioxide warmed the planet in bursts, while sulfur dioxide sometimes reflected sunlight, cooling it temporarily. The result was a climate yo-yo, long-term greenhouse warming interrupted by volcanic winters. If you were unlucky enough to exist in this era, you'd find the weather as unpredictable as a coin toss, except deadlier. One season the skies would bake, another they'd dim under choking haze. Volcanism also played a strange role in ocean chemistry. Lava pouring into seas released metals like iron and magnesium, fueling chemical reactions. Ashfall drifting into the water brought nutrients. Cyanobacteria, those slimy mats clinging to coastlines, found themselves alternately poisoned and fertilized. Sometimes volcanic gases made oceans more acidic, wiping out local microbial populations. Other times the influx of iron-fed explosive blooms, turning shallow seas into bubbling, oxygen-pumping reactors. In a way, volcanoes acted like moody landlords, sometimes smashing their tenants, sometimes giving them bonus food. Here's a thought to make you smile grimly. If you were trying to plan a picnic on Columbia, you'd have about 3 minutes before either lava, ash or toxic air ruined your day. Forget sandwiches, the bread would toast itself whether you wanted it to or not. Still, there's no denying that Columbia's volcanism left enduring marks. Those basalt plateaus once formed, resisted erosion. They became the bones of continents, sturdy platforms that later life would colonize. Magma intrusions carried minerals upward, concentrating copper, nickel, and platinum in ore deposits that humans mine to this day. Every coin in your pocket, every wire in your wall could trace its ancestry back to some furious volcanic event on Columbia. And then there was the spectacle. From orbit, Columbia must have glowed like a wounded animal. Lava rivers streaked across its flanks, volcanic plumes rose kilometers into the sky, and ash bands circled the globe. In the darkness of a billion years, these fiery scars were among the few lights visible from afar. For any extraterrestrial observer, say a curious alien astronomer, Earth would have looked violent, unstable, and strangely alive. Yet through all this chaos, Columbia endured. The continent didn't melt away under the onslaught of lava. It thickened, hardened, and grew more stable. Volcanism was less a destroyer than a sculptor, carving Columbia into something strong enough to last. So, as the fires roar and the skies darken, you realize this paradox. The very eruptions that would have made life impossible for you were the ones laying the groundwork for the future. The crust strengthened, the atmosphere shifted, the oceans stirred with new chemistry. Without those eruptions, Earth's path might have been very different. The mountains groaned, the coasts steamed, and Columbia held together, a supercontinent forged in fire. Now that Columbia had locked into place and endured its volcanic adolescence, the supercontinent settled under a sky that was still more alien than familiar. If you were standing there, mask on, lungs heaving in a thin atmosphere, you'd realize that the air itself was one of the most unstable players in this story. Earth's atmosphere around 1.8 billion years ago was nothing like the breathable mix you enjoy today. Oxygen had only recently begun to trickle into the air, courtesy of cyanobacteria in shallow seas. Before that, the world had been a suffocating haze of nitrogen, carbon dioxide, methane, and assorted volcanic gases. By this point, oxygen levels had crept up to maybe 1–2% of the atmosphere. Not much, but compared to the near-zero levels before, it was revolutionary. For you though, it would be hopeless, like trying to breathe on top of Everest without a tank. 2 desperate gulps and you'd be unconscious. That faint oxygen presence was enough to rust iron in the oceans, enough to trigger chemical shifts across the planet, but nowhere near enough to keep a human alive. Climate during Columbia's reign was shaped by this evolving atmosphere, with carbon dioxide still present in higher levels than today. The greenhouse effect kept the planet relatively warm. Global temperatures averaged higher than modern Earth, though the interior of the supercontinent often swung between extremes, scorching summers and bitter winters. With so much landmass sourcing moist air from the sea, Columbia's heartland baked under dry skies, you'd see red dust storms sweeping across its deserts, coating volcanic plateaus in fine sediment. Along the coasts, the story was different. Here, shallow seas lapped against volcanic ridges and low-lying plains. Warm currents stirred them constantly, mixing oxygen-rich waters with the atmosphere. These coastal shallows became the laboratories of Earth's chemical future. Cyanobacteria spread in mats, layering stromatolites that bubbled oxygen upward. Each bubble was a small miracle, though at the time it seemed almost useless. Most oxygen reacted instantly, with iron dissolved in seawater, precipitating out as iron oxides. Imagine oceans, stained red-brown from this rust, heavy particles raining onto the seafloor in sheets. Over millions of years, these built up into banded iron formations, striped rocks that miners in the 20th century would tear from the earth to make steel. Your skyscrapers, your bridges, your frying pans, all hidden gifts from cyanobacteria 1.8 billion years ago. The atmosphere itself wasn't just warm, it was unpredictable. Volcanic eruptions pumped sulfur dioxide into the sky, reflecting sunlight and cooling the planet for short stretches. At other times, floods of carbon dioxide from volcanic activity supercharged the greenhouse effect. In geological time, this yo-yo of climate seemed stable enough, but if you lived through it, and let's face it, you wouldn't, the weather would feel like a roulette wheel, burning one century, chilly the next. Here's where it gets oddly funny. Imagine you've set up camp in Colombia's desert interior. The sky is hazy, tinted faintly orange from methane and volcanic dust. By day, the sun burns your skin in minutes. No protective ozone layer thick enough yet to filter ultraviolet rays. By night, the temperature plummets, and the wind slices across the barren rock like a knife. Forget bringing sunscreen or a winter coat, you'd need both, and neither would help. Still, despite these hardships, Colombia's atmosphere was stabilizing compared to earlier chaos. The rise of oxygen marked a slow but steady turning point. For the first time, free oxygen lingered in the air long enough to matter. Slowly, ozone began to form high above the planet, building the fragile shield that would one day protect future organisms from deadly radiation. It wasn't thick yet, but it was a start, a thin veil between the surface and the relentless sun. And then there were the storms. With one giant continent spanning much of the equator, atmospheric circulation became exaggerated. Hot air rose in the center, cool air rushed in along the edges, and colossal monsoons battered coastal zones. Picture thunderheads stretching hundreds of kilometers, lightning arcing across black skies, rain hammering shallow seas until they churned like boiling cauldrons. In Colombia's desert heartland, by contrast, storms were rare. When they did strike, they tore the land with flash floods, carving canyons in hours that would last for eons. The interplay between air and rock was relentless. Rain, when it fell, attacked Colombia's young mountains, breaking down minerals into clays and washing nutrients into the ocean. Those nutrients fed cyanobacteria, which in turn released more oxygen. It was a feedback loop, geology feeding biology, biology reshaping atmosphere, atmosphere altering climate, and all of it driven by the vast stage Columbia provided. From orbit, you'd see the difference. Earth no longer glowed in the same lifeless blues and grays. Instead, patches of shallow seas shimmered with hints of green from microbial blooms. Dust veils cloaked the land, volcanic plumes streaked the sky, and the whole atmosphere held a faint, shifting tint, sometimes red from volcanic haze, sometimes blue-green as oxygen crept upward. The planet was halfway between alien and familiar, caught in transition. Colombia's atmosphere and climate may not have supported you, but they were absolutely crucial for what was coming. Every thunderstorm, every lava plume, every bubble of oxygen in a stromatolite was part of the great rehearsal for complex life. The stage was set, the props were in place, the actors just hadn't arrived yet. From the vantage of Colombia's coastline, you turn your gaze outward, not to the land, but to the oceans that surrounded it. These waters stretched endlessly, a global sea encircling the supercontinent, rolling against its volcanic shores and seeping into shallow inlets. If Columbia was the skeleton of Earth's surface, the oceans were its blood, circulating heat, chemicals and life itself around the globe. At first glance, these oceans might look familiar, waves crashing, tides pulling, surface glittering under the sun, but dip beneath, and you'd find something entirely different. The chemistry was alien. Dissolved iron gave the water a greenish-brown tint, like liquid rust. Sulfides bubbled up from hydrothermal vents, turning patches murky and toxic. Oxygen was almost absent in the deep, leaving them anoxic and stagnant. The smell, if you could smell it, would be sulfurous, like rotten eggs magnified 1,000 times. Yet for all their hostility, these oceans were bustling on a microbial scale. The circulation patterns created by Columbia's bulk shaped their ecology. With so much land clustered together, warm equatorial currents flowed, uninterrupted, around the supercontinent, hugging its coasts in vast loops. Cold upwellings rose at higher latitudes, drawing nutrients from the deep. This circulation wasn't just water moving aimlessly, it was Earth's first great conveyor belt, redistributing chemicals and heat across the planet. Imagine hovering above a shallow shelf along Columbia's equator. Sunlight filters down through a hazy atmosphere, warming the waters. In these shallows, microbial mats stretch across tidal flats, forming stromatolites that rise like lumpy steps. Every wave sloshes over them, coating them in sediment that the cyanobacteria trap and bind. Each trapped grain adds a layer, and over time these mats build towers that stand as miniature reefs. No coral yet, no fish weaving between them, just bacteria quietly exhaling oxygen. Further offshore in slightly deeper water, plankton-like microbes drift, photosynthesizing in the sunlit zone. Below them, oxygen fades quickly. The deep ocean remains a suffocating void, full of dissolved metals and methane. This sharp boundary, oxygenated above, anoxic below, shaped everything. It controlled which microbes thrived, where iron precipitated, and how nutrients cycled. Every current that stirred the seas helped spread these layers, redistributing life's limits across the globe. Here's the kicker: those iron-rich waters made the oceans look surreal. Picture the Red Sea, only greener and darker, streaked with red-brown plumes where oxygen met dissolved iron. Whenever oxygen trickled into the water, iron oxides fell out as rust particles, drifting to the seafloor. Over millions of years they layered into banded iron formations, striped rocks of hematite and jasper that geologists today mine for steel. So yes, the steel beams in your city skyscraper, their atoms once sank through Columbia's oceans as rust dust. Ocean currents also delivered nutrients back to the coasts, fueling blooms of cyanobacteria. At times these blooms would have been massive, turning the water surface into green slicks, stretching for kilometers. From orbit, Earth would have looked mottled landmass in the center, ocean bands tinted by microbial life. But don't picture a tropical paradise. The waves that reached Columbia's shores carried more than nutrients. They delivered sulfur from underwater vents, acids from volcanic rain, and heavy metals washed down from mountain belts. If you were foolish enough to swim here, the experience would be brief. Your skin would sting from chemical burns, your lungs would suffocate in minutes, and the taste would be metallic and foul. Forget snorkeling, your mask would fog with sulfur vapor before you even adjusted the straps. But for microbes, this was heaven. Shallow coasts were crowded with life, the first faint echoes of ecosystems. Hydrothermal vents in the deep oceans harbored other microbes, feeding on chemical energy rather than sunlight. Black smokers belched superheated fluids, rich with metals, into the water. Around them chemosynthetic bacteria clustered, forming mats in the darkness. These early ocean communities, though microscopic, were the seeds of future marine life. Currents also sculpted climate. Warm waters carried heat along Columbia's coasts, keeping equatorial zones hot and stormy. Cold upwellings near the poles moderated temperatures there, though no ice sheets existed yet. Seasonal cycles shifted winds and rainfall patterns, just as they do today, but exaggerated by the supercontinent's bulk. Monsoon-like systems drenched coastal shelves, feeding sediments into the sea, while inland deserts baked under cloudless skies. Every grain of sediment washed from Columbia's mountains ended up in these oceans, layering the seafloor with sand, silt and mud. Over time, these deposits thickened into rock, preserving the chemical signatures of the atmosphere and oceans above. Modern geologists read them like diaries, finding traces of oxygen spikes, volcanic events and microbial blooms. Without those layers, the story of Columbia would be lost forever. There's a strange humor here. The oceans were hostile, corrosive, and undrinkable, yet they were Earth's great incubator. You wouldn't last a minute, but microbes thrived, shaping the chemistry that would eventually make the oceans blue, oxygen-rich and alive with fish. Columbia's oceans were like a grim training ground, forcing life to adapt under brutal conditions, setting the stage for everything that would follow. And so as the waves crash on volcanic shores and microbial mats bubble along tidal flats, you realize the oceans around Columbia were not just background scenery. They were the engines of Earth's transformation, endlessly cycling, endlessly preparing for the world to come. Step closer to the shorelines of Columbia, and the rocks tell a quieter story than the thunder of tectonic plates. Here, in shallow pools and on tidal flats, you see the true architects of change: microbes, tiny cyanobacteria, invisible to your naked eye, but unstoppable in their effect. They spread in films over wet rocks, layered like slimy green carpets. Over generations they trapped grains of sediment and secreted sticky mucus that built domed mounds. These are stromatolites, Earth's first reefs, modest in size but world-shaping in consequence. If you crouch over one of these microbial mounds, you'd see faint streams of bubbles rising. Oxygen. Not much, not enough to fill your lungs or fuel even a single insect, but for the first time in billions of years, free oxygen is seeping into the water and the air above. It's easy to dismiss these mounds as dull, but their chemistry was radical. Until then, Earth's atmosphere had been suffocating, a greenhouse stew of methane, nitrogen, and carbon dioxide. Now slowly, drop by drop, Oxygen was accumulating, at least locally. But there's a catch: most of that oxygen didn't last. In Columbia's oceans, dissolved iron lurked everywhere. Whenever oxygen appeared, it reacted instantly, forming rust particles that rained onto the seafloor. Imagine the ocean turning cloudy, streaked red-brown as particles sank. Over millions of years, they built banded iron formations, striped rock layers of iron oxide alternating with chert. If you pick up a piece of that banded rock today, polished and gleaming red and black, you're literally holding the fossilized breath of microbes from Columbia's coastlines. These microbial mats weren't confined to just the shallows. They spread wherever sunlight reached the seafloor: coastal shelves, lagoons, tidal flats. They dominated ecosystems for hundreds of millions of years, building stromatolite structures meters high. And though they lacked drama, you'd hear no animal cries, see no movement beyond faint rippling in the slime. They were rewriting the planet. Their relentless photosynthesis pushed oxygen production higher, year after year. The interiors of Columbia weren't completely lifeless either. Microbes colonized rivers and lakes that pooled in rift basins, forming mats along mudflats. Some specialized bacteria thrived without oxygen, feeding instead on methane or sulfur compounds. These anaerobes filled niches where oxygen never reached, proving that life wasn't limited to just one chemistry. In Columbia's time, microbial diversity was already branching into different strategies: sunlight harvesters, methane eaters, sulfur reducers. They formed invisible food webs long before predators or prey existed. There's humor in realizing that the landscape of life in Columbia's world was more about slime than spectacle. No forests, no grazing herds, just mats of goo clinging to every wet surface. If you slipped while walking across a tidal flat, you'd land face first in a bacterial carpet, older than any dinosaur or oak tree, hardly Instagram-worthy, and yet that slime was more revolutionary than anything to come for 1 billion years. The microbial expansion also changed the oceans themselves. Local blooms of cyanobacteria could make the water green and cloudy, clogging shorelines. When they died, their remains sank and decomposed, consuming oxygen and sometimes leaving waters below anoxic again. These cycles of bloom and die-off reshaped chemistry in pulses, like a heartbeat. Over time, oxygen began lasting longer in surface waters, even as the deep ocean remained suffocating. This uneven distribution of oxygen created a world of contrasts: shallow shelves, rich in microbial mats and oxygen bubbles; deep basins, dark and toxic. And yet, every layer of sediment told the same story: progress. Oxygen was no longer just a fleeting experiment. It was becoming part of Earth's system, slowly accumulating in the air and water. By 1.8 billion years ago, oxygen concentrations were still low, maybe 1–2% of today's levels, but that was enough to tip chemical balances. Toxic gases like methane began to diminish. Iron precipitated out of the seas in massive deposits. Even the sky above Columbia may have brightened, shifting from a reddish haze to a paler, bluer tint as oxygen rose. From your vantage, the scene is paradoxical. The land is silent and barren, the seas greenish and metallic, the life forms invisible without a microscope. And yet, the changes unfolding here are monumental. Every microbial mat you see is a miniature factory, pumping out molecules that will one day let trees grow, birds fly, and you sit comfortably with oxygen in your lungs. Without these mats, Columbia would be just rock and ocean forever. So you watch the slimy pioneers spread across the coast, their bubbles floating skyward. They don't look impressive, they don't move, they don't roar, they don't build civilizations, but they are patient, and patience is their weapon. Columbia's microbes are not just surviving, they are transforming the planet, one oxygen bubble at a time. By now you've seen Columbia's microbes bubbling oxygen into shallow seas, but to understand their true impact, you need to rewind a little to the Great Oxidation Event, which had kicked off hundreds of millions of years earlier, around 2.4 billion BC. By the time Columbia took shape at 1.8 billion BC, Earth was living in the aftermath of that atmospheric upheaval. Oxygen wasn't just a quirky byproduct anymore, it was becoming a force that restructured the planet. Before oxygen rose, Earth's surface chemistry was dominated by methane, carbon dioxide, and sulfur gases. Methane, in particular, acted as a powerful greenhouse blanket, trapping heat and keeping Earth warm under a fainter sun. When cyanobacteria began to photosynthesize, they churned out oxygen that tore apart methane molecules. The greenhouse blanket thinned. The result? a massive global cooling that plunged Earth into some of its earliest ice ages, the so-called Huronian glaciations. You can picture glaciers crawling across continents, oceans freezing over, and the entire biosphere teetering on the edge of collapse. By Columbia's era, the ice had retreated, but the planet was scarred by the event. Oxygen lingered in the atmosphere at maybe 1–2% of today's levels, fluctuating with microbial productivity. For you it was still deadly thin, but for Earth it was revolutionary. For the first time, free oxygen was available in the environment, altering the rules for chemistry, geology and biology. One of the clearest consequences was written into the rocks. As oxygen met the ocean's dissolved iron, it precipitated out as rust, forming massive banded iron formations, BAs. These stripy red and black rocks are Columbia's geological signature. Imagine layer after layer stacking on the seafloor, red iron oxides, alternating with silica-rich chert, built like the pages of an endless stone book. Today, miners dig them up in places like Western Australia and Canada, turning them into the steel that builds cities. Without those ancient microbial exhalations, your skyscrapers, cars, and even cutlery wouldn't exist. But oxygen didn't just paint the oceans red, it rewrote the biosphere. For anaerobic microbes, those that thrived without oxygen, the rise of O2 was catastrophic. To them, oxygen was poison. Whole populations suffocated, shrank, or retreated into oxygen-free refuges like deep sediments and hydrothermal vents. It was in effect the first global extinction event, wiping out entire lineages of microbes that had dominated for billions of years. Imagine being one of those organisms, thriving for eons, only to be outcompeted by slimy newcomers belching a deadly gas. A tough break. Yet out of that crisis came opportunity. For other microbes, oxygen was a jackpot. It allowed far more efficient energy production compared to anaerobic pathways. Cells that adapted to use oxygen could extract many times more energy from the same nutrients. It was the evolutionary equivalent of trading a bicycle for a jet engine. These oxygen-tolerant microbes laid the groundwork for the complex life that would come much later. On land, though, land was a barren word at this point. Oxygen began to react with surface minerals. Iron in rocks rusted. Organic carbon in soils oxidized. Even volcanic gases reacted differently once oxygen was around, producing new atmospheric chemistries. Slowly, Earth's redox balance shifted, moving the whole system closer to what you recognize today. From your imaginary perch above Columbia, you'd notice the difference in the sky. Before, the atmosphere had been hazy, reddish, heavy with methane. By 1.8 billion BCE, it was clearer, thinner, perhaps with a bluish tinge in places. The sun's light penetrated more directly. Clouds formed differently, shaped by higher oxygen and lower methane. The view was still alien, but it was moving toward familiar. Of course, oxygen didn't rise in a smooth curve. It surged and crashed, tied to the rhythms of microbial productivity, volcanic activity, and ocean chemistry. Sometimes oxygen levels spiked, other times they plummeted. Geologists call this the oxygen overshoot and oxygen crash cycles. Picture Earth as a teenager testing boundaries, breathing heavily one moment, sulking in silence the next. Columbia's oceans were the laboratory where these fluctuations played out, and the effects rippled everywhere. Nutrient cycles changed. Sulfur compounds behaved differently, recorded in isotopes that geologists still study today. Trace metals like molybdenum and copper became more available, fertilizing microbial evolution. Without those metals, key enzymes for complex life would never have formed. Here's where you pause and grin. All of this chaos, poisoned microbes, rusted oceans, frozen continents, was caused by what looks to you like pond scum, not towering beasts, not dramatic meteor impacts, just tiny mats of cyanobacteria working slowly, stubbornly, endlessly. Columbia's coastlines might have looked dull, but they were stage sets for the most radical planetary makeover in history. So, as you breathe your safe modern air, remember this: every lungful is a gift from Columbia's microbes. You wouldn't be alive without their ancient rebellion. With Columbia fully assembled and its microbes rewriting the air, the next story carved into its crust was the rise of vast mineral and resource deposits. If the supercontinent was a stage, then tectonics was the set designer, shoving, melting, and welding rock until the foundations of Earth's future industry were laid. You can almost hear geologists today cheering, because the riches hidden in Columbia's rocks, iron, copper, gold, nickel, are the very resources modern civilization depends on. Start with the iron. You've already seen how cyanobacteria's oxygen rusted the oceans, raining iron oxides onto the seafloor. Over tens of millions of years, this created banded iron formations, biafs, so thick they stretched across entire cratons. In Columbia's era, these deposits piled up in basins along the Canadian Shield, in Western Australia, in Brazil, and in Africa. Today, miners blast them out of the ground in Pilbara and Carajás, turning them into steel beams and rebar. Every time you walk into a skyscraper or step onto a bridge, you're standing on the fossilized exhalations of Columbia's microbes. But iron wasn't the only treasure. The mountain belts formed by Columbia's collisions acted like pressure cookers, squeezing and heating rocks until metals concentrated into ore veins. Gold and copper traveled with hot hydrothermal fluids, filling fractures in metamorphic zones. Imagine quartz veins shot through with sparkling streaks of metal, cooling slowly in the deep crust. Billions of years later, prospectors would stumble across them, digging the veins that fueled ancient empires and modern economies. Then there's nickel and platinum. These came not from mountain building but from deep magmatic intrusions. When mantle plumes pierced Columbia's crust, they carried molten rock rich in heavy elements. As that magma cooled, metals segregated into concentrated layers. The Sudbury Basin in Canada, today one of the world's richest nickel sources, has roots in this era. Even meteor impacts, slamming into Columbia's crust, sometimes added to the mix by melting vast volumes of rock and redistributing metals. Stand in Columbia's time and you'd never suspect this mineral wealth. The surface looked barren, bleak, and lifeless, but beneath your boots, the crust was being stacked with riches. To your eye it was just dull grey stone. To a geologist with the right hammer and microscope it was treasure. It's worth remembering that minerals don't just sit there passively. They fed into Earth's evolving chemistry. Trace metals like molybdenum, copper, and zinc, leached from Columbia's crust by rivers, washed into the oceans. Microbes gobbled them up, building enzymes that made photosynthesis more efficient and oxygen production more stable. In short, Columbia's mineral veins weren't just future mines, they were fertilizers for life's next chapters. Picture rain falling on Columbia's mountains. The water rushes down slope, carrying sediments and dissolved ions. Streams converge into rivers, which empty into shallow seas. There nutrients spread out, feeding blooms of cyanobacteria. More oxygen is released, more iron precipitates, more sediments bury the seafloor. Over millions of years, this constant cycling carved geochemical feedback loops. Rock nourished life, life altered the air changed the way rock weathered. Columbia's mineral systems were not static, they were gears in Earth's great machine. And then tucked away in the margins, other oddities formed. Columbia's tectonics produced greenstone belts, zones of ancient volcanic and sedimentary rock metamorphosed by heat and pressure. These belts often held gold, forming lodes that would later become famous mining districts. Elsewhere, basins trapped organic matter that over immense spans of time turned into early petroleum-like deposits. These weren't the coal or oil fields humans tap today, but they were chemical precursors, hints of the energy reservoirs to come. Here's a fun irony. Columbia itself would be long gone by the time humans arrived, but its legacy would literally power modern industry. The steel in skyscrapers, the copper in electrical wires, the nickel in batteries, the gold in wedding rings, all trace their origins to the tectonic convulsions of this forgotten supercontinent. When you charge your phone tonight, you're plugging into Columbia's ghost. If you could somehow pick up a rock in Columbia's time and crack it open, you might glimpse shiny flecks in quartz veins, or dark bands of magnetite and hematite. To you they'd mean nothing, you'd be too busy suffocating in the thin air, but to future civilizations, they would mean everything. Columbia was in a sense the planet's first great bank, a vault of minerals built by tectonics, microbes and time. And so you stand there, staring at bare rock under a sulfur sky, not realizing that billions of years later, this desolate landscape would fund space programs, skyscrapers and electric cars. Columbia's crust was barren at the surface, but rich in ways that only time could reveal. Columbia may have felt indestructible once it locked into place, but no supercontinent is forever. Beneath its thick crust, the mantle never stopped stirring. Convection currents kept churning, plumes of hot rock rose, and stresses began to build in the very foundations that once held the landmass together. By about 1.6 to 1.3 billion years ago, the first signs of strain were clear. Columbia was starting to crack. Imagine standing on one of its interiors, dry, barren, a desert of stone. and watching the ground split under your feet. Rifts stretched for hundreds of kilometers, valleys sagging downward as the crust pulled apart. From these fissures, basaltic lava spilled, coating the land in black plains. The air shimmered with heat, sulfurous gases hissed upward, and the supercontinent's skeleton groaned under the tension. You'd think Columbia was coughing in its sleep, trying to shake off the pressure locked inside. The causes were deep and relentless. Mantle plumes, those columns of abnormally hot rock, punched at the base of the crust like blowtorches. Where they rose, they thinned Columbia's underbelly, making it prone to rifting. At the same time, the sheer weight of such a vast landmass pressed down unevenly, causing some regions to sag while others bulged upward. Picture a massive, rocky quilt stretched too tightly across a restless bed. It couldn't stay flat forever. Faults began to open, splitting crust that had once been sutured together during Columbia's assembly. Along those faults, earthquakes rattled the surface, some strong enough to shift whole blocks of land downward into rift valleys. These valleys, often filled with water, forming long inland seas. In places they became traps for sediments and microbial mats, preserving new layers of rock that geologists still study today. Each rift was both a wound and a record. One of the most dramatic signs of stress came from large igneous provinces, LAPs. These were not ordinary eruptions, but cataclysms, flood basalts covering hundreds of thousands of square kilometers. In India's Darwar Craton and Canada's Shield, you can still see the remnants. At the time they would have looked like hellscapes, fountains of lava spouting from fissures, rivers of molten rock spreading faster than you could outrun, skies darkened by sulfur-rich ash clouds. Forget building a hut here, your neighborhood would be swallowed before you finished stacking rocks. All this volcanism pumped greenhouse gases into the air, warming climate in bursts, but over long time scales the weathering of fresh basalt drew carbon dioxide out again, cooling things back down. Columbia's climate became a pendulum, swinging between warmth and chill, as geology and chemistry wrestled for control. For microbes clinging to tidal flats, these swings were both opportunities and crises. Sometimes nutrients poured into the sea, feeding blue. Other times chemical changes poisoned them, yet through it all, the mats endured, stubborn as always. As rifts deepened, some fragments of Columbia began to drift. Laurentia, Amazonia, Baltica, each tugged at the seams. By around 1.5 billion years ago, the cracks had grown into wide bisons, and pieces were inching away. It wasn't a sudden collapse but a long, slow unzipping. In geologic terms, Columbia was losing its grip. Still, it didn't vanish overnight. For millions of years it clung together in patches, shifting and stretching. Think of it like an old puzzle left in the rain, the edges warping, the pieces loosening, but the overall picture still recognizable. From above, Columbia was still the largest feature on Earth's surface, but its fate was sealed. It would slowly transition into its successor, Nuna, sometimes called Hudsonland, and much later, Rodinia. Here's the irony. The very processes that tore Columbia apart were the same ones that built it. Mantle convection and subduction assembled the puzzle, and mantle plumes and rifting dismantled it. The supercontinent cycle assembly, stability breakup was already in motion, a rhythm Earth would repeat many times. Columbia was simply the first verse of a song still playing. If you were hovering above in imagination, you'd see bright volcanic scars streaking its surface, fault lines spidering across cratons, coastlines reshaping, rivers shifted courses, inland seas opened, and microbial mats adapted to new environments. To a human eye, it would look like disaster. To Earth, it was business as usual. And so Columbia entered its twilight, not in a single fiery explosion, but in the slow grind of tectonic inevitability. Its mountains eroded, its faults deepened, and its crust began to scatter. A supercontinent that once seemed unbreakable was already unraveling, setting the stage for the next in Earth's endless sequence of continental giants. Columbia's unraveling didn't spell the end of supercontinents, it was only the transition to the next act in Earth's grand tectonic cycle. By about 1.5 to 1.3 billion years ago, the seams that once held Columbia together were gaping wider. Its fragments drifted, rotated and reconfigured, eventually merging again into what geologists sometimes call Nuna, or Hudsonland, and later evolving toward Rodinia. You could say Columbia was less dead than rebranded, its pieces reshuffled into new configuration. Imagine watching the map of Earth in time-lapse. Laurentia, which anchored Columbia's core, begins sliding away from its neighbors, carried by conveyor belt subduction zones. Amazonia, Baltica and Siberia drift too, though their paths are differently depending on the push and pull of underlying mantle convection. One craton may drift north, another rotates, a third collides elsewhere. The supercontinent's familiar quilt is coming undone, but the fabric itself remains intact, just rearranged. As Columbia fragmented, rifts widened into new oceans. Along their margins, volcanic activity raged. Each spreading center pumped out basalt, creating young seafloor. Subduction zones formed elsewhere, consuming old ocean crust and setting up future collisions. This dance of rifting and subduction is the heartbeat of Earth's tectonic system, and Columbia's breakup was one of its earliest full rehearsals. The transition into Nuna wasn't dramatic in human terms, no single event marked it, but over 100 million years, the pieces coalesced into a different arrangement. By around 1.3 billion years ago, Nuna was recognizable, still containing many of Columbia's original cretons, but assembled differently. The cycle of unity and separation had played through its first full round. From your vantage point, the changes are striking. Rivers that once drained into Columbia's interior basins are now redirected toward widening rift valleys. Mountain belts, once central, are eroded into lowlands as tectonics shifts elsewhere. New coasts emerge, irregular and volcanic, as the continent's edges tear apart. Imagine a shoreline that once lay deep inland suddenly becoming the edge of an ocean, one of those bizarre cartographic shifts that only plate tectonics can manage. Rodinia would come later, around 1.1 billion years ago, but its seeds were already sown in Columbia's demise. The same cretons, Laurentia, Baltica, Amazonia, Australia, and others continued their restless wanderings, destined to collide again. Think of it as continental recycling. The crust never vanishes, it just rearranges. Your favorite neighborhood creton could one day be part of a different supercontinent altogether. Here's a wry thought: if you had tried to plant a flag on Columbia to claim permanent territory, your land would have drifted thousands of kilometers by now. Imagine explaining that to your descendants. This used to be Columbia, but now it's Nuna, and soon it'll be Rodinia. Don't worry, we still own the creton. Plate tectonics laughs at human ideas of permanence. What's fascinating is how these transitions influenced Earth's systems. The breakup of Columbia created new coastlines, shallow seas, and sediment traps. These environments expanded microbial habitats, allowing life to spread further. Oxygen continued to fluctuate, sometimes rising with bursts of productivity, sometimes falling when oceans stagnated. Every tectonic rearrangement tweaked the chemistry of both sea and sky. Even the mineral story continued. As new collisions forged Nuna, fresh mountain belts rose, generating more erosion, more sediments, and more ore deposits. The crust was recycled not just in motion, but in resources. Columbia's death was, in a sense, the birth of new geologic opportunities. From above, you'd see Earth's surface evolving like a restless puzzle, pieces separating, edges glowing with volcanism, oceans widening, and yet, through all the motion, the underlying rhythm was steady: assemble, stabilize, rift, break apart, reassemble. Columbia was simply the first supercontinent to complete that rhythm, proving that Earth's crust operated on a cycle as ancient as the mantle itself. So as Columbia faded into Nuna and paved the way for Rodinia, it left a legacy not of permanence but of pattern. The Earth had revealed its tectonic pulse, a cycle that would continue through Pangaea and beyond. Columbia may have been the first, but it certainly wouldn't be the last. With Columbia giving way to Nuna, and eventually paving the path toward Rodinia, the focus shifts to something even more profound: the effect of these continental shuffles on life's trajectory. It's easy to think of tectonics as only geology, rock smashing into rock, but in reality the assembly and breakup of supercontinents dictated the stage upon which biology could play its slow microscopic drama. The most immediate influence was on nutrient cycles. Every mountain range Columbia produced eroded into rivers, delivering minerals like phosphorus, molybdenum and iron into the seas. These trace elements weren't trivial, they were the raw materials for microbial enzymes. Without molybdenum, for example, cyanobacteria couldn't have performed nitrogen fixation, one of the most critical biochemical tricks for sustaining life. Without iron, photosynthetic pathways would have faltered. So every storm that wore down Columbia's peaks fed the microbes that in turn fed the atmosphere with oxygen. Tectonic activity also determined where shallow seas formed, and shallow seas were everything. They were warm, sunlit, nutrient-rich environments where microbial mats flourished. stromatolites stacked higher, and oxygen production ramped up. When Columbia was intact, its vast coastlines created long continental shelves, prime real estate for cyanobacteria. Later, as rifting split the land apart, even more coastlines formed, multiplying these habitats. In a strange way, Columbia's breakup may have been just as important as its assembly, because every new ocean basin meant more shallow water nurseries for microbes. Then there was the oxygen paradox. While microbes pumped O2 into the air and water, tectonics decided whether it stayed there. Volcanic outgassing consumed oxygen as it reacted with gases like hydrogen sulfide and methane. Weathering of fresh basalt also drew oxygen down, binding it into minerals. Only when Columbia's cycles slowed enough did oxygen stabilize in the air. These push and pull dynamics, dictated by geology, set the tempo for the biosphere. Too much volcanism, and oxygen crashed. Too little and it rose. Life's options were bound to this rhythm. The effects rippled further. As oxygen slowly stabilized, it created the possibility for more complex single-celled organisms. Around the time Columbia was breaking apart, the first eukaryotes, cells with nuclei, appeared in the fossil record. They didn't explode in diversity yet, but their emergence was no accident. Oxygen-rich microenvironments made it possible for cells to handle higher energy loads, and tectonically driven nutrient fluxes supported their evolution. In other words, Columbia's geology indirectly lit the fuse for the eventual rise of plants, animals and you. Think too about climate. Supercontinents altered how heat and water circulated on Earth. Columbia's massive interior was arid and harsh, but its breakup introduced more coastlines and more rainfall. Changing circulation patterns affected monsoons, storms and even glaciations. These swings created selective pressures for microbes. Some thrived in oxygenated waters, others retreated into anoxic refuges. Diversity increased, not because of predators or competition, but because the Earth itself kept reshuffling the rules. Here's the irony that makes you chuckle softly. Microbes ruled Columbia's world, yet they had no idea they were rewriting the script for future life. To them, oxygen was just waste. To anaerobes, it was poison. To future multicellular organisms, it would be a lifeline. Every bubble that rose from a stromatolite in Columbia's shallow seas was both a death sentence to some lineages and a gift to others. You wouldn't call it intentional, just chemistry and chance, but the outcome was destiny. Columbia's cycles also remind you that life and geology were never separate. Mountains crumbled, feeding seas. Microbes bloomed, altering air. Air shaped weather, weather eroded rock, and the loop fed back endlessly. If you tried to pull apart biology and geology, you'd fail. On Columbia, they were threads in the same fabric. Standing on one of its coastlines in your imagination, you'd see nothing impressive. No forests, no fish, just slime and rust-colored seas. And yet you're looking at the hinge of history. Without Columbia's tectonic engine, Earth might have stagnated, locked in a barren state like Mars. With it, the biosphere grew richer, inch by inch, toward complexity. So yes, Columbia eventually broke, scattered into new continents. But in its lifetime, it didn't just build mountains, it built possibilities. Every crack, every river, every shallow shelf was a scaffold for life's next steps. The supercontinent's geological restlessness became biology's greatest gift. As you've followed Columbia's birth, growth and eventual fracture, you've probably noticed a pattern. Supercontinents are not one-time events. They are chapters in a longer supercontinent cycle. Earth's peculiar habit of pulling its landmasses together, ripping them apart and starting over again. Columbia was the first we can reconstruct with reasonable confidence, but it was only the beginning of this planetary rhythm. Think of it like breathing. Earth inhales, continental fragments drift together, collide, and fuse into a supercontinent. Then Earth exhales, the landmass fractures, new oceans open, and continents scatter. The cycle takes hundreds of millions of years for each breath, but over the planet's history, it has repeated several times. Columbia was followed by Nuna, then Rodinia, then Pannotia, then Pangaea, and eventually the continents you recognize today. And even now, Earth is already setting up for the next one, sometimes nicknamed Amasia or Nova Pangaea in speculative reconstructions. Comparing Columbia with its successors shows both similarities and quirks. Like Columbia, Rodinia, about 1.1 billion years ago, gathered many of the same cratons into a different configuration, sprawling across the equator. Later, Pangaea, about 300 million years ago, repeated the pattern on a grander scale, pulling nearly all modern continents into one landmass. In each case, the same forces were at work: subduction consuming ocean crust, collisions welding cratons, rifting tearing them apart. But Columbia's uniqueness lies in its timing. It was the first complete supercontinent after Earth's atmosphere had been radically altered by the Great Oxidation Event. It demonstrated how supercontinent cycles interact with climate, oceans, and life in profound ways. Pangaea gave you dinosaurs. Columbia gave you oxygen. Without it, those later spectacles wouldn't have been possible. From a planetary perspective, the supercontinent cycle acts like Earth's thermostat. When continents assemble, weathering of tall mountains sucks carbon dioxide out of the atmosphere, often cooling the planet. When they break apart, volcanic activity and seafloor spreading pump carbon dioxide back in, warming things up. Columbia, in its long existence, likely drove both cooling phases and greenhouse swings. These tectonic breath cycles explain much of Earth's climate stability over billions of years. Without them, Earth might have frozen solid or boiled into a Venus-like hothouse. It also explains why Earth is so different from Mars or Venus. Those planets lack active plate tectonics, and so they lack supercontinents. Mars froze into a cold desert. Venus baked under a runaway greenhouse. Only Earth, with its restless surface, kept reshaping itself, creating the conditions for life's persistence. Columbia wasn't just a lucky accident, it was the proof of concept that supercontinents were integral to habitability. Of course, if you try to imagine living through Columbia's cycle, the humor comes naturally. Every 100 million years or so your continent would change neighbors. One century you're attached to Amazonia, the next you're drifting towards Siberia. Borders, meaningless. Real estate, forget it. Your backyard would literally move thousands of kilometers. Complaining about zoning laws would feel quaint compared to watching your house rift into a new ocean basin. Scientists today piece together these cycles using paleomagnetism, the tiny compasses preserved in minerals that record the orientation of Earth's magnetic field at the time they formed. By comparing these signatures across cratons, geologists can reconstruct how continents moved. For Columbia, those clues come from places like Canada, India, and Brazil. Every magnetic grain is a breadcrumb leading back to the first supercontinent cycle we can see with clarity. And that's why Columbia matters. It wasn't just a one-off mega landmass, it was the template. It set the precedent for how continents would behave for the next 2 billion years. It showed that landmasses aren't static, that Earth is a restless planet, and that the cycle of assembly and breakup is inseparable from climate, atmosphere, and biology. So when you think of Columbia, don't picture a lonely barren continent lost in deep time. Picture the first verse of a planetary song, a rhythm of collision and fracture, of mountains rising and oceans flooding, of oxygen blooming and life adapting. Columbia's place in the supercontinent cycle is the reason the Earth you stand on today even exists. Columbia may have broken apart long ago, its outlines erased by time and its mountains worn down to stumps, but its legacy is still written into the modern Earth. When you stand on the Canadian Shield, hike across the Pilbara in Western Australia, or walk the Iron Ranges of Brazil, you're standing on fragments that once welded together to form that first supercontinent. The rocks beneath your boots are the direct descendants of Columbia's crust, still carrying the scars of collisions that happened 1.8 billion years ago. Geologists trace those scars in the form of ancient suture zones where cratons slammed together and fused. They see them in twisted belts of metamorphic rock, in granitic intrusions, in greenstone belts, rich with gold. These aren't just abstract relics, they're practical resources. Columbia's tectonic drama concentrated minerals into ore bodies that humanity mines today: iron from banded iron formations, nickel from magmatic intrusions, copper and gold from hydrothermal veins. All of it ties back to Columbia's violent assembly. The backbone of modern industry is built from Columbia's ruins. Even Earth's geography today still whispers Columbia's name. The stable cratons that form the heart of continents, Laurentia in North America, Amazonia in South America, Baltica in Europe, the Kapval in Africa, the Pilbara in Australia, were all part of that first continental quilt. Their survival through billions of years is why continents exist at all. Without Columbia's stabilization of these cratons, Earth's crust might have remained thin, unstable, endlessly recycled by volcanism. There might have been no dry land for forests, no stable shelves for shallow seas, no foundation for civilizations. The supercontinent cycle Columbia inaugurated also continues to shape the world. Pangaea, the most famous of its descendants, only formed because Columbia proved that global land masses could assemble. Today, as continents drift on their slow tectonic courses, geologists predict they will reunite in another 200–300 million years to form a Masia, or Novo Pangaea. In that sense, every modern map is just a snapshot in Columbia's long echo. Columbia's oxygenation legacy is even more profound. The bubbles released by cyanobacteria along its coasts created the iron formations that built our cities, yes, but they also laid the foundation for breathable air. By the time Columbia fractured, oxygen had risen to levels that made the first eukaryotes possible. From there, the path to complex life was open. Your lungs, your beating heart, your brain's electricity, all of it depends on the atmospheric chemistry Columbia helped shape. There's a certain dark humor in realizing this. You live in a world of skyscrapers, smartphones, and highways, but the true architect of your existence was slime clinging to tidal flats on a barren continent billions of years ago.